All right, guys. In the next few videos, I'm just going to go through the released AP Chemistry FRQ questions from this year's May 6th exam. And I'm saying that because the students at West Springfield, we haven't taken the AP Chemistry test yet. We're taking it on the second date, the May 21st date. So this is just extra review for you guys that haven't taken it yet. And anyone who's watching this who's not at West Springfield, then hopefully, if you took the test on May 6th, hopefully you did well, and and hopefully you got all the correct answers. So this video, I'm going to go through question one, and then a quick overview of what I thought, and then we'll go through question one, and then we'll get into the rest of the questions in the subsequent videos. Okay, so overall, I thought it was a pretty straightforward test. I didn't think there were any kind of trick questions, any gotcha questions, anything like that. I thought it was pretty straightforward. There was a QSP, KSP question if you're trying to find the precipitate, and they kind of walked you through it. They forced you to do M1V1 equals M2V2 for one of the ions right off the bat in that question, and then they gave you the answer to M1V1 equals M2V2 for the other ion before you plugged in for your Q calculation. So I thought, kind of if you're reading through the questions carefully, they kind of guide you through it. And let me just scroll through the test here and just see if there were other things that kind of, no, I didn't think it was that bad. I overheard people that had taken the test complaining about the phosphorus pyramid or something, and I didn't really understand what they were talking about until I saw the question. And again, like I tell my students, don't get upset if you've never seen this in your AP chemistry class and go and give up on the question. All this is a simple dot structure question, and all you really needed to do was put a lone pair on each of the phosphorus and you're done. It was a very simple question, but again, they're going to throw stuff that you haven't seen before, but it's all testing the same content that is covered by everybody. So you just got to trim through all the fat and get to the guts, the meats of the question, and answer accordingly. So I saw that. After I went back, I made my answer key, but then after I went back and looked at this question, I thought maybe this would be a question where they might try to get you on significant figures because you have to do the subtraction for the delta T. And when you do the subtraction here, you end up with 2 sig digs for your delta T answer. So maybe, but they didn't mention anything about significant digits directly in the question. So usually when they are testing on sig digs or significant figures, they remind you within the question that to make sure. So I don't know about that one, but I'll show you either way. This one, when I made my original answer key, I miscounted. All you had to do was count the particles, and for some reason I counted 3 of these, the PCl3s, but when you go back, there's only 2 of them in the container. So, simple mistakes like that can happen to anybody, and it happened to me when I first went through this. Okay. And then when I was going back to double check my answer key, I totally didn't answer 5D, and it's just because I just skipped over it. I didn't even see the question. I was coming back through it, and then I was reading this question, 5 part D, and I realized I hadn't read it before. I hadn't even read that question. So I was like, there's an ideal gas law question on the test, and yeah, there was, and I just skipped right over it. Distracted by other things and that kind of thing. So, make sure you read every question. Like D is a very easy, all you're doing is plugging your numbers. If you remember to convert your Celsius to Kelvin, it's a really simple point to get right here. And I thought the galvanic cell one, the electrochemistry one, I thought that was very straightforward. And we didn't have to do any electrostoichiometry. Maybe kind of with part C, maybe your calculation that you did, you might do a calculation with, you know, coulombs or something like that, but that would be kind of a stretch, and you'd be, but not a stretch, but you'd have to be making up a lot of stuff that you don't have to do for part C. So really no electron stoichiometry or anything like that. So this one can be tricky, this last one, but again, not super tricky, just a little bit. Okay. So for my students, this test, there were 43 prompts. Sorry about my really bad handwriting here, but question 1 had 10 prompts, so we know each one of those prompts is worth 1 point. But question 2 only had 8 prompts, so 2 of the questions are going to be worth 2 points. It's hard to tell which 2 are going to be the ones that are worth 2 points. I have an idea of in question 3 which one I might think might be a 2-pointer, but I'm not sure. So question 3 only had 9 prompts, so one of them is worth 2 points. But the shorter questions, question 4, 5, 6, and 7, they each had 4 prompts apiece. So you know it's just, you know, one point for each one. So you know that's something to think about. And this is strictly for my for West Springfield AP students. I thought the majority of the test, so 23% of these prompts related to Unit 1. Our Unit 1, okay? So again, this is just West Springfield High School, not anywhere else. Our Unit 1 was a big part of the test, so, you know, make sure you're reviewing your Unit 1 stuff. Unit 3 was a big part of it, and Unit 5, acid base. The other big part was Unit 6. It was 14% of the exam. Unit 7, only 7% on this. For ours, okay? So anyway, so let's get into question number 1. So again, whoops, here we go. Let's just see what the question looks like, and then we'll get into the answers. Okay, so we start off with a mass spec question, and it's pretty straightforward, right? So they give us the percent abundance here, and we should understand that they should add up to 100%. And so we have 1% abundance, and we're missing 2 of them. And we're told it's 79%. So, you know, obviously the missing percentage is 21%. So that means these 2 isotopes account for 21% of the isotopes. And we're told that they're approximately equal. So if we just take, you know, 21 and divide it by 2, that means this would be 10.5%, and this would be 10.5%. So if we look at what I drew, so you got to go up to 10.5 and 10.5, 10.5 of a piece. But again, kind of thinking about it, the percent abundance needs to add up to 100%. So we had 79% accounted for, so 100 minus 79, we have 21% missing. And we were told it was evenly distributed between the remaining 2 isotopes. So just take the 21, divide it by 2, 10.5. So magnesium 25 is around 10.5%. Magnesium 26 is around 10.5%. Okay. In question 2, in part 2, they ask us what the difference between magnesium 25 and magnesium 26 is. So basically, what's the definition of an isotope? You know, so magnesium 25 has 1 more neutron. Or sorry, magnesium 26 has 1 more neutron. Okay, I don't think you have to get this detailed. I think you could just say magnesium 26 has 1 more neutron than magnesium 25. But if you want to add a little bit more detail, right, it's, you know, that number that you're given is the mass number, which is protons plus neutrons. Since they're magnesium, they have to have the same number of protons. So what's the difference? Different number of neutrons. Okay. So when we get to the next, whoops, let me move that over. Okay, so the next question, it's talking about the ion dipole interactions between magnesium and water. Okay, so they show that, right? So here's a magnesium ion, and then, you know, the oxygen is the negative dipole of water. So we got our ion dipole interactions between magnesium and oxygen in the water. And then it's asking why a sodium ion, kind of in the same position, would have a weaker interaction. And we need to use Coulomb's law. Now remember, this year is kind of the first year they're giving us Coulomb's law here on the formula sheet. And it's reminding you that the force of attraction is proportional to the charge 1 times charge 2 divided by the radius between them squared. But they don't say radius, they say the separation between them. So what Coulomb's law is telling you is that the higher the charge, the stronger the attraction. So the higher the magnitude of charge, the stronger the attraction. And the smaller the radius, right? The smaller the particle is, the closer they can get to each other, the stronger the interaction. Okay, that's what Coulomb's law says. And it maps it out for you. It says, explain why the magnesium, the sodium to magnesium, or sorry, the sodium to water interaction is weaker than the magnesium to water interaction in terms of charge and in terms of radii, okay? So size, all right? So we got to know that magnesium has a 2 plus charge and sodium has a 1 plus charge, so higher magnitude of charge, so that answers part 1. And then for part 2, we should know that magnesium 2 plus is slightly smaller than sodium 1 plus because they both have the same electrons. They have the same number of electrons as neon. Okay, they both have the same electron configuration as neon, 1s2, 2s2, 2p6. So they have the same number of electrons, same energy shells around them, but magnesium has 1 more proton in the nucleus, and that pulls the electrons closer, making it have a smaller radius. Okay, so we would say, you know, we're referencing Coulomb's law. The higher the charge, a higher magnitude of charge, the stronger the attraction. So since sodium's 1 plus and magnesium's 2 plus, that's why magnesium's going to have a stronger interaction. And then sodium has a larger radius than magnesium ions. And the reason that is because magnesium has a greater nuclear charge, a plus 12 nucleus versus a plus 11 nucleus. And so that means magnesium ions are going to be able to get closer to water and thus have the shorter the distance between the opposite charges, right? Think of it. The closer magnets get to each other, the stronger the attraction. And so since magnesium is going to be able to get closer because it has a smaller radius, it'll have a stronger interaction because of that, okay? So part C, calculate the pH of the solution in beaker 2. So beaker 2 has sodium hydroxide. We have to understand that, and we have the molarity of the hydroxide. The negative log of hydroxide is POH, and then we're going to have to subtract from 14 to get the pH. So all we have to do is take the negative log of this number and then subtract from 14, and we're golden, right? So negative log of hydroxide equals POH. And remember that it's on your formula sheet, right? So let's go, right? If you forgot, I mean, hopefully by now in your chemistry career, you have this on lockdown, right? You don't have to reference your formula sheet, but POH equals the negative log of hydroxide, and then pH plus POH always equals 14, so we're good to go. All right. So then we get the POH, and then 14 minus this is 10.447, so that's the pH. Okay. Whoops. All right, and then we're going to part D. Okay, so part D, we got a solution of magnesium nitrate, and we're given its molarity and volume. We got a solution of sodium hydroxide and its molarity and its volume, and it looks like we're mixing them all together, right? Now notice here in the question it says assume the volumes are additive. So when it's mixed, the final volume is 50 plus 35, so the final volume is 85 milliliters or 0.085 liters. And the student, so it says the student combines these two solutions as shown in the diagram. We want to calculate the magnesium concentration. Remember, when you see something in brackets, that means the concentration of it after 2 solutions are combined, but before any reaction takes place. So if there's any precipitation, we're talking about before that. So everything's still dissolved. All that's changed is the volume. So this is perfect candidate for M1V1 equals M2V2, a dilution equation. And you want to be careful. I'll go back here. Like, we don't have to really be careful because it's asking for the magnesium concentration, and because the subscript of magnesium is 1 over here, that means the molarity of the salt is the molarity of magnesium to start with. So M1 for magnesium is this number, okay? But if we were doing M1V1 equals M2V2 for the nitrate, M1 would not be this number for the nitrate. We would have to take this number and multiply it by 2 for it to be the M1 for the nitrate, because there's 2 nitrates for every 1 magnesium nitrate, okay? So just kind of a FYI for, maybe that'll happen on the May 21st exam, okay? Oops, all right, let me pause that. All right, so we just do M1V1 equals M2V2. Again, our final volume was 85 milliliters. Remember, when you're doing this proportional equation, you can keep the volume in milliliters. You don't have to convert to liters, but you could have done 0.35 times the molarity initially to figure out how many moles of magnesium you had to start with, and then divide by 0.085 liters to get the new molarity. Same thing. All right, so the new molarity of magnesium after it's mixed is 7.62 times 10 to the negative 4. Don't forget your units. It's molarity, it's capital M, or you could do moles per liter, or maybe moles times liters to the negative 1, okay? In the next question, they show us the dissolving of magnesium hydroxide. So understand, like the forward reaction would be magnesium hydroxide dissolving, but the reverse reaction would represent magnesium hydroxide precipitating. And if you're thinking, if you're thinking ahead of the game, we're mixing magnesium nitrate with sodium hydroxide. So, based on our solubility rules, we probably wouldn't be thinking sodium nitrate precipitates, because that's a very soluble compound. But hydroxides are usually insoluble. They're very soluble when they're paired up with an alkali metal, but when they're paired up with an alkaline earth metal, right, the second group, maybe not as soluble. Hydroxides aren't very soluble usually. So the possibility of mixing these 2 solutions together could trigger magnesium hydroxide to precipitate, right? But anyway, they give us the dissolving of making a solution of magnesium hydroxide. They give us the KSP for it, so the equilibrium constant for this process. And part 1, write the equilibrium expression. Now remember, it's been a while since Unit 4 and all of our equilibrium stuff, but remember, you don't include solids in the equilibrium expression. And KSPs are always just solids dissolving in water, solids dissolving in water. KSPs never have a denominator. So, I was walking around watching some people, do this as some practice this morning, and I saw some people have KSP equals magnesium times hydroxide squared divided by magnesium hydroxide. No denominator for KSP expressions. And make sure you say K equals or KSP equals the expression, right? And remember, the squared comes from the coefficient of hydroxide, okay? So this would be the expression. And then in the next part, it's asking us to see if we're going to see a precipitate. So this is doing a QSP calculation and comparing it to KSP, okay? And we already calculated the magnesium concentration that we should plug into our QSP expression. It's our answer from part D, right? And then they told us what the hydroxide is. So they did the M1V1 equals M2V2 calculation for us for the hydroxide. So this is what we're plugging in for hydroxide, and we have the magnesium concentration for part D. We plug them into the KSP expression, but it's a Q calculation because these are our initial concentrations, and we want to figure out, are we at equilibrium, or are we oversaturated, or are we undersaturated? Will we see a precipitate, will we not? Okay, but don't forget, you're going to have to square this when you plug it in the expression because it's the concentration of hydroxide squared, okay? So we plug those numbers in, we get our QSP. All right, QSP came out to be something times 10 to the negative 11, and KSP was 10 to the negative 12. So QSP is greater than KSP. If QSP is greater than KSP, that means you have too much product, meaning you're oversaturated these ions. The reaction is going to shift to the left and produce the solid reactant here and give us our precipitate. So since QSP is greater than KSP, yes, we'll see a precipitate because we were oversaturated, okay? Then we get to part F. In a separate experiment, the student adds some nitric acid to decrease the pH of the saturated solution containing undissolved, so solid magnesium hydroxide. Does this addition change the amount of undissolved magnesium? Meaning, does adding the nitric acid cause more of the magnesium hydroxide to dissolve? And the answer is yes. So, so does the amount of undissolved magnesium hydroxide increase, decrease, or remain the same? It increases, okay? The amount of, the amount of undissolved magnesium hydroxide decreases. More of it dissolves. It's just a weird way to word it, but more of it has to dissolve. And the reason that is because this is a strong acid. The nitrate's not doing anything, but the H plus will take out hydroxide. So adding the H plus will lower the concentration of hydroxide, causing the reaction having to shift this way, so causing more of the solid to dissolve. So you'll end up with less undissolved or more dissolved magnesium hydroxide, okay? So the amount of undissolved magnesium hydroxide will decrease because the H plus you're adding will take out the hydroxide and form water, right? Acid-base neutralization. And that's gonna shift the reaction, right? If the concentration of hydroxide decreases below the point of saturation, more of the magnesium hydroxide would have to dissolve to get it back up to the point of saturation, okay? Okay, so that's question 1 on the free response for this year. Hopefully you got them all right, and you got 10 out of 46 points. And I'll be on in the next video to go over question 2.